All right, today we are going to jump into a fundamental rule in probability that seems super simple on the surface, but trust me, it trips almost everyone up at first. It's all about dodging a very common, very intuitive mistake. Let's see if you can spot the trap. Okay, here's a quick puzzle for you. In a class of 100 students, you've got 40 who know Python, 30 who know Java, and 10 who know both. So how many students know either Python or Java? Go with your gut. What's the first number that pops into your head? If you immediately thought 70, hey, you are in good company. It just feels right, doesn't it? You take the 40 Python folks, add the 30 Java folks, and boom, 70. Simple math. But here's the thing. That simple answer is wrong. You've just walked right into one of the classic pitfalls in probability, the double counting trap. That number, 70, is actually hiding a pretty big error. So let's break this down. Let's figure out exactly where that simple addition goes off the rails. This right here is the heart of the problem we need to fix. Let's trace our steps, shall we? First, we count the 40 students who know Python. Easy enough. Then we go and add the 30 students who know Java. But wait a minute, what about those 10 students who know both languages? Well, they were in that first group of 40, and then we counted them again in the second group of 30. We've counted them twice. So how do we fix this mess? Well, the hero of our story is a simple but incredibly powerful tool: subtraction. We need a proper rule that actually accounts for that overlap. And here it is in all its glory, the general addition rule. It says the probability of event A or event B happening is the probability of A plus the probability of B minus the probability of both A and B happening. That little minus sign at the end, that is everything. It's the whole correction for our double counting problem. Now, what do these weird symbols even mean? That U shape, that's the union. Just think of it as uniting the two groups together. It simply means we want the probability of A happening or B happening or even both. And then there's this one, the upside down U. That's the intersection. This is our overlap, right? It's the probability of A and B happening at the exact same time. So in our little classroom problem, these are those 10 students who are fluent in both languages. Okay, so let's apply this to our original problem and get the right answer. We take our 40 Python students, we add the 30 Java students, and now for the crucial part, we subtract the 10 we counted twice. And there you have it. The real answer is 60. You know, the formula is great, but to really truly get it, you gotta see it. And this is where the good old Venn diagram becomes your best friend. I mean, this quote just nails it. Imagine one circle for Python students and another for Java students. When you take the area of that first circle, you're including the bit that overlaps in the middle. Then, when you take the area of the second circle, you include that exact same middle part all over again. See? To get the true total area, you have to subtract that overlap one time. So the big takeaway here is that this rule is for events that can overlap. But what about when they can't? Think about flipping a coin. You can get heads or you can get tails, but you can't get both at the same time. We call those mutually exclusive events. In that case, the intersection, the overlap, is just zero. So the formula simplifies right down to just P of A plus P of B. This simple rule is really just a special case of this bigger general one. Okay, so this is way more than just a fun classroom puzzle. Understanding this rule is absolutely critical in fields like engineering and computer science, where the stakes can be, well, a lot higher. Let's look at a server. Let's say the probability of its CPU failing is 20%. The probability of its RAM failing is 10%. And the probability that both fail at the same time is 5%. The really important question for an engineer is, what's the probability that at least one of these things goes wrong? And that phrase, at least one, that's our big clue that we're talking about, a union. So using our rule, we add the individual probabilities and we subtract that overlap. 0.2 plus 0.1 is 0.3 minus 0.05. That gives us a 25% chance of system failure. Now, think about this. If an engineer just blindly added the probabilities, they'd get 30%, a dangerous overestimate of the risk. That could lead to wasting time and money on a problem that's less likely than they think. And this logic, it shows up everywhere in tech. It's used to calculate the real reliability of a complex system. It's at the core of how database queries with OR conditions are optimized. It even helps developers understand how much of their code is actually being tested when they run multiple overlapping test suites. So to wrap all this up, let's just make sure we have the two core concepts, union and intersection, totally locked in. Getting these straight is absolutely key. Okay, let's do a quick side-by-side. Union is your OR keyword. It means at least one of the things happens. On a Venn diagram, it's the total area of both circles combined. Intersection is your AND keyword. It means both things happen together, and it's just that little overlapping part. So the union usually makes the probability bigger, while the intersection makes it smaller. And here's a little pro tip for you. When you're reading a problem and you see keywords like or at least one, or any of these, a little light bulb should go off in your head. That is your signal that you're dealing with a union, and you probably need to use the general addition rule. Look, if you only remember one thing from all of this, let it be this. The number one most common mistake is just forgetting to subtract that overlap. So before you ever add two probabilities, just stop and ask yourself one simple question. Can these two things happen at the same time? If the answer is yes, you have to find that intersection and subtract. So we've pretty much nailed this rule for two events. But what happens when things get even messier? What if you have a CPU failure, and a RAM failure, and a network failure? How do you avoid all the different ways of double counting then? Well, that's a question that opens up a whole new, fascinating level of probability.